Start talking about it, even if you're not quite done. Let's engage in the conversation and let's learn from this. Hey guys, okay, so I'm going to work on it up here. At the end of the day, I need y'all engage in this conversation. I get it that we haven't done a ton of this. However, we did do some of this, and I know that I sounded frustrated to some of y'all because I am frustrated that we didn't even go look at the notes that we took yesterday when we practiced in part A on this exact style of question. Because if you had just written this out already, this is no different than what we did yesterday. Guys, use your resources. Some of us right here were able to do it without looking at our resources. I saw you glancing over at someone else's board some though, Parker, and not learning, just copying. Copying ain't going to help you on a test because we're going to be in rows. It's going to make it really hard for you to copy off of somebody else. Okay, so instead of that, let's just learn and grow and focus. Like when I look up here, how many factors can I multiply at a time? 2, okay? Some people are really comfortable distributing straight from here and not drawing out what to help you multiply, the area model. But guys, I would draw that area model every time, personally. Like, as someone who used to do this, as someone who can actually do the majority of this in my head without writing anything down, you know what I still like to do because it makes my life easier? The area model. Guys, the area model is a good visualization. It helps me not make mistakes. It can help me go from factored form to standard form. But x times x is x squared plus 2x plus 2x plus 4. And then remember, this is another reason why I like it, because it shows my like terms in those diagonals. And so these two factors multiplied together gave me x squared plus 4x plus 4. And now it's times x plus 2. And so now you just have to do another area model. You can do it vertically, as most of y'all did, I think. Oh, well, no. I guess only 2 groups got to it. Yeah, y'all did it vertically. But remember, in this factor right here, can you let it run in? In this factor right here, how many terms are there? 3. There's 3 terms, right? So how many rows or columns does that factor need? 3. So it doesn't matter if I do it vertically or horizontally. There's my 3 terms. How many rows then do I need for x plus 2? 2. It's just x plus 2. Guys, I'm trying to break it down to a way that if you slow down and you just think through, hey, I'm multiplying, so I need to use that area model to help me multiply, anybody and everybody can do it. You get out your resources, practice, and engage in this conversation. Again, I'm just multiplying. I have 1x here, I have 2x's here. If I multiply 1x by 2x's, how many x's do I have? 3. 3 being multiplied, x cubed, plus 4x squared, plus 4x. Because it's x times each of these. Now 2, say again? Yeah, it's the last one on there. Okay? Plus 8x plus 8. And then I just add my like terms. So, f of x is equal to what? X cubed, 6, x squared, plus 8. Please remember, I'll always put a plus or a minus on the inside, because remember I'm adding those terms. I'm multiplying the factors, but adding my terms. And the whole idea is that this is equivalent to x plus 2 cubed. Someone made the comment yesterday, I don't remember if it was in here or not, they're like, man, 3 lines, that's crazy. No, just remember, if it's 3 lines, it's not equal to, it's what? Equivalent, yeah. So whenever I use those 3 lines, it's very intentional to say, hey, these may look different, but they are in effect they may look different here, but they're in effect the same. The same inputs are going to map to the same outputs if I've done my work correctly. So how can I check to make sure I did my work correctly? Okay, what I want you all to do, I don't have my calculator up yet. I want you to go get a calculator if you don't have one yet. I want you to check and make sure that these two things are in fact equivalent. Every teacher today is going through to this ACT stuff to talk with a company we have coming in. And one of the things that they talked about, a lot of good things, one of the things they didn't talk about is this idea of equivalence. Guys, on the math side of things, I kid you not that almost 10% of the questions of every ACT are somehow related to equivalence. If you know how to check equivalence, you can get those right every single time. So grab a calculator, check your equivalence. While you check equivalence, I'm actually going to pass out the check your understanding. Y'all, I need you to actually do something, guys. You're capable of a lot of things. Yeah. Were you cutting with like a saw or with yeah.
What do you mean by law?
Huh?
Coming from the law. That's in test mode. Can you see these off your computer?
Say again?
Can you look at these calculators off your computer?
I have them set up for the day for that. Thank you, Jaw. I appreciate it. Yep. Come on, Maya. Graph those two functions, check see if they're equivalent. Victoria, check your standard form and your transformed one, your parent function one. See if they're equivalent.
Oh, Michigan.
Oh, yes, sir.
When you get time, can you come here real quick?
Do you need to sign my name?
I need to see if I can mark it in the attendance book. Jaw, is that last one not working?
No, we did B yesterday, but we haven't B this one.
What you see is the practice one skills. That one not working? Yeah. Okay, so.
It gave me the look. No, it didn't give me a parabola. It said it because it didn't.
Oh, I was saying, should it give you a parabola? No, why should it not give us a parabola, guys? Because it's a cubic, not a what? Quadratic. If it's squared, it's quadratic. You as well? Yours wasn't working?
No, well, I need extra anyway, but she didn't have it.
I don't have any more right now. I mean, you can ask Ms. Granberry, I guess. Ms. Williams, make sure you get it right back. Alright, so Rihanna, that was yesterday for you. Jaden, when was yours?
11:20.
Yep.
But it's so old.
No, I just got it yesterday.
I was saying, was it parent excuse or doctor excuse?
Mine of it.
Right, but there was
Don't
that
you hate
Thanksgiving
it
break.
twice?
Well, remember, that was the week before Thanksgiving break.
Thursday, Friday, Monday. It was due Monday. I brought it.
Alright, so x cubed.
I'm just saying.
Alright, so we're going to talk about a couple of things with this that I need to pay attention to. So, first off, were we correct? Did we correctly multiply this out?
Yes.
Yes. Hey, where's any of the erasers? Can you toss that to me? Thank you.
Right, you just bought some, they obviously.
Well, I took them home for ACT prep and then I forgot to bring them. I put an alarm on my phone today. Alright, Walter. Actually, I need a
Oh,
alarm.
wait, bring it back?
They're at minus.
Bring him back.
All
I got him
right,
again.
so, are they equivalent?
Yes.
I got it, I'm good. Oh, because you have 2 over there? Yeah. Well, y'all need an eraser, right?
Yes, sir. Third jump. Oh, yeah.
Okay, so are they equivalent? How do we know? Hey guys, how do we know they're equivalent? Huh?
There's only one.
They
It
match.
look like one.
So,
line.
it looks like one, now be careful, not one line, because that's not a line, right? What is that? What could we call that? We could call it a cubic function, we could call it a curve, we just can't call it a line because it's not linear,
We can call
okay?
it a sequence.
Huh?
Not two sequence.
No, not a sequence. Okay, so it looks like one function because it mapped to itself. We need to recognize it's mapping to itself, so we would just say it is equivalent, same input, same map to the same outputs. Now, there was something I was going to say with that. Oh, building on what we talked about yesterday. So if this is a cubic, right? How many roots should we see? Or how many roots are there? Right? So the degree is 3, so there should be 3 roots by the what? What tells us because its third degree has 3 roots?
By X.
There was a really important thing that was fundamental to algebra.
What's the initials?
Huh?
First letter.
It's pretty fundamental to, I don't know, algebra. Say again.
The fundamental theorem.
The fundamental theorem of algebra, right? So, remember, we wrote about this on Monday, we recapped it yesterday. The fundamental theorem of algebra is what connects the number of roots to the degree. So it's third degree, it's 3 roots. I need y'all to pay attention to that though, because it is that fundamental theorem of algebra, not just the x, we have to connect it with the fundamental theorem of algebra. By the way, 1, 2, 3, 4, 5 people with hats/hoods, take them off. Why are we acting like this is a Mr. Kinney rule? I personally don't give a dump, but we all know that that's against the rules for Hillcrest High School. Am I wrong? Okay. KB. Hood and hat. Thank you. All right. So, the next thing I want to talk about though is how many roots do you actually see on that graph?
You know, man. 2.
One.
Say again.
X squared plus.
I only see 1. On that graph, where's the 1 root? -2. Why do we know -2 is a root? So it's in x-intercept. Remember, my real roots show as what? X-intercepts. Not just any intercept, an x-intercept. So I only see 1 real root there. But I'm supposed to have how many?
2.
3.
Supposed to have 3, right? So where's my other 2? Maybe imaginary, right? What can I use? I need y'all to pay attention to this. I need you to write this down. This is something you may need to add on to that Frere model. That was not the one I just handed out, the one from yesterday that we took notes on about multiplicity, right? So, Rihanna, the part about multiplicity you missed yesterday, this is what we're about to cover. It's in the bottom left, I think.
Oh, what's that?
The Frere model that I gave you on Monday for
How many
notes.
times did it appear?
Those are my bottom.
Probably, yeah. So, here's the thing. What can I always use to find my roots? It's like I can't always see them on a graph. What do I need to use? Huh? Okay, a table could be helpful, but have we actually even done anything with tables this unit? No, I can't see it graphically. I need to look at the... No, I haven't done anything with the picture. Huh? Okay, yeah, these are... We have a graphical polynomial, we have an algebraic polynomial. Say again. No, it was a... I don't even know if I said unit 5, but it's talking about creating polynomials. You guys, what else do we have besides a graph? We also have an... Thank you. We have the equation, guys. Right? We got this equation. Hopefully you don't need to write anything. You might want to add something though if you aren't seeing this right now. Well, Rihanna, you need to add this because you weren't here yesterday. Hey guys, I have my equation right here. What can I do to find my roots? Say again, Dee Dee. Maybe eventually, but we can't use inverses yet. Set it equal to what? Hey guys, remember, what's another word for a root? A zero. We want to recognize. I'm asking for roots or zeros. Now what can I do? Could I do what Dee Dee was saying about using inverses?
Yeah.
What tells me, Finney, that we can use inverses here?
The vertex one.
Be careful. If it's a cubic, does it have a vertex?
No.
It is a transformation of a parent function, which is what a lot of us are thinking about. But it's not that. There's another detail here that I talked about several times. What allows me to know, hey, I could use inverses in this case?
Zero. Anything equals zero equals zero.
Anything multiplied by 0 equals 0. That's the zero product property and for factored form. But no, I'm saying, what allows me to use inverses here?
The zero.
The cube.
How many times we see it?
How many times do you eat?
Yes, how many times do you see the variable? How many times do you see that variable up there?
Once.
Once, so what can we use? Inverses, okay. I need us to recognize, guys, if we see the variable one time, we can use inverses. That's going to work whether it's a quadratic, whether it's a logarithmic, whether it's a cubic, whether it's anything you want. You can use inverses as long as there's only one variable shown. You can use it at other times as well, but that will always definitely work. But I'm going to rewrite this. What is x plus 2 cubed again? Okay, x plus 2, what, 3 times? Added, subtracted, multiplied? Multiplied 3 times, okay. Now, Finney, this goes back to what you were saying earlier. What can I use now? Okay, we need to recognize, like, zero product property is available to us. So what could x plus 2 equal? This first factor? 0, okay. What could the second factor, x plus 2, equal? What about this one?
0.
All right. Notice in each of these equations, I see the variable once. So what does x equal? Negative 2. How many times does x equal negative 2? It equals it. No, sorry. I messed up. Hold on. X equals negative 2. X equals negative 2. X equals negative 2. How many times does x equal negative 2?
3 times.
Okay, so how would I write that? X equals negative 2 with multiplicity of 3. And so, Rihanna, I know you weren't here yesterday, but just looking at this, thinking it through, logically, why are we saying it has a multiplicity of 3? Well, it's not just that. You're going back to the original. I'm talking, just look right here. Why are we saying it has a multiplicity of 3? Okay, and not just the x 3 times, it's that we see x equals negative 2 3 times. It's how many times that root is a root. Because like if it says x equals 2, I wouldn't say a multiplicity of 4, I would say x equals negative 2 with a multiplicity of 3, and x equals 2 with a multiplicity of
1.
How many times do you see x equals 2?
1.
So it's a multiplicity of 1. Guys, your multiplicity is just how many times you have that root. So please remember, make sure you have this in your notes, the multiplicity of a root is how many times a root appears. So I will say, so a lot of times people are like, oh, it's the same, so it's going to be 3. Make sure you actually work it out, solve for your roots. However many times that root appears, that's the multiplicity. Can I pause you really quickly, Abby? Okay. So this sheet that I passed out, this check your understanding, okay? This has you doing 2 different things. If you pay attention to the instructions, it says determine the multiplicity of each 0, then determine the standard form. You can practice trying to sketch it. I'm not going to sweat that detail. It's what I was asking students to do last year with that. I'm not asking you all to do, okay? But find your zeros, find the multiplicity of your zeros, and get the standard form. That is practicing these 2 things, and that is something you desperately need to make sure you know how to do. So, we good on multiplicity. Questions about multiplicity? And zero reaction. Let's say I work out a polynomial, and I get these as my roots. Okay, got 4 roots here. Alright, Brianna, here's my 4 roots. What's the multiplicity for x equals 2?
1.
So I got 4 roots up there. I'm gonna just let Brianna think about it for a second.
I can barely see the thing, but okay.
So,
You said what's the question?
what's the multiplicity for x, the root x equals 2? That's a multiplicity of 2. Why?
You see it twice.
You see it twice. X equals 2, 2 times, right? What's the multiplicity for x equals negative 1, Finney?
1.
Multiplicity of 1. Okay? KB, what's the multiplicity for x equals 3? You think it's 3?
Give me 1.
Why is it 1? Why'd you switch?
Wait, you confused me. What?
Why do you think the multiplicity is 1? Confident in that answer?
3.
You think the multiplicity is 3?
Yeah.
Okay, let's put it to a vote. Raise your hand if you think the multiplicity is 3. So Jaden does, Ivan does. Raise your hand if you think the multiplicity is 1. So a lot of us are thinking multiplicity of 1. Let's get some opinions about why.
Are we using that?
Huh?
Are we using that?
This one right here. Yeah, Chelsea, what do you think the multiplicity of x equals 3 is? Say it louder. Why are you thinking 1?
I mean, I would say 1 because 3's up there once.
Right.
How many times do we see x equals 3?
Once.
1 time. What's the multiplicity?
1.
1. Not trying to trick you. We need to know however many times we see x equals 3, that's my multiplicity.
Oh, is that simple?
It's that simple.
Okay, I got it now.
However many times you have that root, that's your multiplicity. Okay? Now, one thing I do want to remind you of before we before we move to the next part of this lesson today, please remember how a function behaves at these different multiplicities. If the multiplicity is 1, what does that function do at that x-intercept? Anyone remember? Not sure? Okay, let me ask this a different way. If the multiplicity is 1, does it go through the x-intercept or does it bounce?
Bounce.
When the multiplicity is 1?
It doesn't matter.
It was bouncing when it was
More than one.
not just more than 1. Yesterday specifically when the multiplicity was 2. So like right here at x equals 2, it will bounce. But here at negative 1 where the multiplicity is 1, it's going to go through, it's going to bounce, and then it's going to go through. Why is it going through here? Because the multiplicity is? No, going through.
Oh,
When it goes through, the multiplicity is
1.
1. When does it bounce?
Yeah, twice.
Multiplicity is 2. Now I do want you to see this, and this is why I want you to be careful. Chelsea, I think you were the one that said when the multiplicity is more than 1, right? But right here, what's the multiplicity at this root? X equals, was it negative 2, multiplicity of 3, right? When it was 3, did it bounce? No, it went through. What you'll learn is, at some point, I'm not going to test you on this right now, we might get into it some more if we have time, but what you'll learn is, if the multiplicity is 1 or 3, or any other guesses what other multiplicities will it go through? 5, 7, 9. If the multiplicity is odd, it's going to go through. The only difference is how much does it curve at that root. So when is it going to bounce? When the multiplicity is 2, or 4, or 6, or 8, etc. If the multiplicity is even, it's going to bounce. It's just how flat is it gonna get around that x-intercept? So it might be a good idea to make a quick note of that. If the multiplicity is odd, it goes through the x-intercept. If the multiplicity is even, it bounces at that x-intercept. So if multiplicity
Where are we writing this?
is bottom left where it talks about multiplicity and zeros. Zeros and multiplicity.
If it's even, it's out.
Yes. So whether it's going through or bouncing at that x-intercept. That's what we need to pay attention to. Only thing I'll point out is it's going to go down, right? Because it's not going to stop there. No, it is going to go through. Yeah, it's going to go through. We'll talk more about this later. Put it through. So have you ever seen a polynomial bounce like this, or does it kind of have like a smooth curve? Like think about the vertex of a parabola. It's not exactly the same, but it's similar. But also, we're going to learn something about that more, Walter, probably Friday. So you don't stress the graph yet. Abby, we're going to like check for equivalence on there, but don't graph it yet, because I'm going to teach y'all how to graph it once you find your roots and what's called the end behavior, stuff like that. So don't do the graph yet. All right. So hopefully that was a good recap of multiplicity. We understand multiplicity a little bit better.
Yep.
We know how to multiply our polynomials a little bit better using that area model to get the standard form. Okay? And Brian, I know you may be comfortable with it already, just if you go to get the notes from anybody else, this is where we convert polynomials to standard form. That's where we're using that area model to multiply. We just can only multiply 2 factors at a time. Alright, pass out to check your understanding. Agenda for today, while y'all are wrapping up your notes with that, we're going to get into something called How Hot is Janelle's Coffee? We're going to use this to recap some details about how to analyze a polynomial. And what I mean by analyze, I mean look at the features of a polynomial. When you look at a polynomial graph, what are some features we've looked at for those polynomial graphs?
Degrees.
So that's it's not really a feature on the graph, and it doesn't even have to be a polynomial, we'll say.
On the graph.
Yeah, on the graph.
Other kinds of balances.
Well, that's not something we've done in the past, is it? That's something we're doing now. Keep thinking. What are some aspects of the graph? Maybe think about the parabola. What were some features of the parabola that we looked at? X-intercepts and y-intercepts. Those might be important. Okay. In Algebra 1, did you ever talk about like the highest points and the lowest points on a graph? Yeah, what were those points called? Maximum and minimum. Yep, so we're going to talk about that some. Earlier this year when we did transformations, we talked about all the inputs and all the outputs. What were those called? One started with a D, the other one started with an R. Domain and range. We're going to talk about that. So all of those things will be some recaps. We're going to introduce one idea with that. So almost everything you've done before, we're just going to introduce one new idea with it. Okay, just as a heads up, and if we finish this, when we finish this, we're going to do some practice with these ideas.
Yeah.
Just as a heads up, tomorrow I will be at the University of Alabama leading some professional development. So I will be out. You will have a Delta Math assignment, and I have to figure out if there's anything else I'm going to put with it. But You do have a sub, he'll be here tomorrow, and we'll work from there. It's Mr. Dykes.
Who is Mr. Diamond?
You had him before, I thought.
Is he like a
Yeah,
math teacher?
oh no, he came in after school, or not after school, afternoon.
Is
one
he
time.
just a regular sub or he a real math teacher?
He's not a math teacher, but he is very intelligent. He's good. He's more history focused. I know he's teaching adjunct at UA for history next semester, so very intelligent, can be very helpful. But again, it's also Delta math. It'll be
That's all we're doing.
all about, I think there might be something else I have to decide after class today. It'll be domain and range. It'll be maximum and minimum and stuff you can do.
That's it.
No, I mean, it'll be practice with that. All right.
Let's make that it.
We'll see. Okay. Really quickly, I want to point this out. This is on the second page of Open Up Resources. I'll be brief on this. Please notice Max here said x plus 2 cubed is equivalent to x cubed plus 8. What did Max do to go from here to here?
Area model.
Did he? Is that what you got when you did the area model?
Nope.
Not even close. What do you think Max did? He did what? He did 2 cubed and x cubed. He tried to distribute the exponent. Please hear me very clearly on this, guys. You cannot just distribute an exponent, okay? You can distribute an exponent when you're multiplying, but not when you're adding like this. If you graph this, it will not be correct. And there's a quick way to know this. If you're thinking about transformations, how would that plus 2 transform the function?
Left 2.
This would be to the left 2. How would this transform that function?
Up 8.
Why would this one be up when the other one was left?
It's not inside the defining operation.
So yeah, remember when it's inside that defining operation, remember how it was horizontal? That was the h in our quadratic. When it's outside that defining operation, that is vertical. So would those be the same thing at all? No. Guys, please hear me clearly on this. One of the most common mistakes, Parker, one of the most common mistakes students make is they try to just cube the x, and cube the 2. You can't do that. To cube means to multiply 3 times. You have to use the area model. Okay? But again, on like the ACT, you can check equivalence by just graphing. Alright. Alright, so how hot is Janelle's coffee? So, Janelle is heating up a cup of coffee in the microwave. This is the sheet I just passed out to help us understand the features of a polynomial. The temperature of the coffee in her mug measured in degrees Fahrenheit from when she first put it in the microwave to when she finished drinking her cup 10 minutes later is shown in the graph below. Here's the graph. So, what I want you to do is I want you to work through with your small group at vertical surfaces, doing your best to answer these questions. We're going to go over them later. The only thing I don't want to see is standing around doing nothing because everybody can come up with an answer. So, think through what was the temperature of the coffee when she first puts it in the microwave. Think about what feature that is. Answer it. Describe how the temperature changed during this 10-minute interval. So let's get up, let's talk through these things. We'll come back and discuss soon. Are you for real? You gotta, okay. You played a dangerous game there. Alright, let's get up to our vertical surfaces. Let's answer the questions 1, 2, 3, etc. Yes, 4's are right there. Jax, you're going to be over on the left over here. Yeah, there we go, the 8.
When she first puts in the microwave, it's 75.
Alright, so please go on back to your groups and let's discuss. Hey guys, don't erase it, just let's talk about this in our groups, okay? Okay, well, sorry, go back to your groups, Dean, and let's talk through some of these details. So, what I want you to do is, I know some of us have already started to fill it out. If you've already filled it out, get out a colored pencil or a colored marker out of the boxes. So like there's a box underneath there. If you don't have a box near you, there's one back there, one back there. So get a colored pencil or a colored marker. You actually need 2 or 3 each to be able to annotate it. You can also use a pen. Now, we'll say a marker would probably be a better option to highlight some things. No, because I want you to be able to clearly tell what I'm telling you to add on to.
You said
Well,
that better to use a
not
marker.
that box.
I don't know. Go ahead.
What?
You get the marker.
Okay?
Just bring the box with you.
You said it's better to use a marker.
No one's sitting right here right now?
Lean in.
We just need a couple colors.
So,
You think that, you said we need 3 colors?
what up, Joe? I would do 3 colors each.
If you lean out, you plug them.
I got you.
Free can.
There you go, you take that one. I got 3.
You got 3 colors. Okay?
I don't need one.
I'm glad that works.
Okay, but well, I'm gonna ask you to highlight some things on your graph. That's for you, well, I guess it's not for you and job. Yes, you need some? How about this, if you need some, where's a desk that no one's sitting at?
Right here.
Thank you. If you need some, quickly go grab some from here, so that you can highlight things, please just don't knock over that. Okay? Okay? I think this was Jack's, y'all write it right here. You're gonna have to erase number 4, I think I can leave everything else though. Alright, now, here's what I wanna add on to, and this is why I wanted you to have a marker to be able to add some details to notice. So, just about everyone, I think, successfully recognized, number 1, what was the temperature of the coffee when she first put it in the microwave? 70 degrees. How did we know it was 70 degrees? Like, what on the graph told us that?
The bottom
Starting point.
The bottom start point.
Why
There's
is
another
that?
term I'm looking for. Say it again.
Why is
Hey
that?
guys, we're talking about these graphs and these functions. That starting point is my what? Y-intercept, right? So y-intercept of 0 what? What's the 0? No, what is the x value, but 0 what? What is that x value indicating? 0 minutes. Guys, when we talk about functions, we're not just talking about random numbers, especially if it's representing the real world. 0 minutes, comma, 70 what? So the temperature though is degrees Fahrenheit. Notice that's conveying a lot more information, right? 0 minutes into this whole situation, her coffee's at 70 degrees Fahrenheit. It's telling a story. Okay, from there. All right, number 2, it says describe how the temperature of the coffee changed. Now, this is actually right here why I wanted you to have some markers. So, y'all did a great job of talking about some of these things, but I want to add on to this. What happened first to her coffee?
It increased.
It's increasing. What's increasing?
How high
The temperature, okay? So I need you to take one of your markers, okay? And I need you to highlight. Tell me when to stop because it stops increasing.
Stop.
Stop right there? Okay? So this is what we would call an increase, meaning the y values go up. Okay?
What our markers do that.
So highlight your increase there. Alright?
You said we need 3 colors.
Yeah, so we're going to use other colors for other stuff, okay? So yeah, it's increasing. The y value is literally going up. Okay?
Yes, sir.
I will point out, what kind of slope would this have here? Let me rephrase that. Would this have a positive or a negative slope?
Positive.
It would have a positive slope, right? So why is it increasing? Because the slope would be positive. Yeah, right? We need to recognize whenever there's a positive slope, it's increasing. Man, is it cold in here? Or is that
Yes, it's cold. It's already like 20 degrees outside.
Oh my gosh. You're on the feet back there. Okay, so we got this increase. The y values are going up, the slope is positive. So what happens after that point?
It
It
decreases
decreases,
slowly.
right?
But like
So-
slow, not slowly though, not like.
Where
It
is our?
decreases slowly. We'll talk about that a little bit more closely later. So here it is decreasing, right? Meaning the y values go down. All right. So we've got this idea of increase, decrease. It's actually going to be really, really, really important later. So hold on to these ideas. I'll explain when we get to the third color in a second. Now, here's what I want to point out, okay? And I need y'all to hear me clearly on this. A lot of y'all did a great job on number 2, starting out saying, so describe how the temperature changed. So the temperature, what?
Increasing.
Increase.
To 170.
Uh-huh.
Fahrenheit, from 0 to 1.5 degrees, then decreases.
But I'm gonna actually pause here for a second, because I wanted, y'all all talked about the increasing from 70 to 170, which is the most common thing that students wanna do when talking about increase. But what did I talk about over here with the kings? What did I ask y'all to add on to?
From 0 minutes to 1.5.
From 0 minutes to 1.5 minutes. I need y'all to hear me clearly on this. By saying it increases, I know it goes up. The question is, where is it going up? Yeah, it goes up from 0 degrees, or 70 degrees to 170 degrees. For 0 minutes to 1.5 minutes. You can add that detail of the temperature in there, but notice I did not, what's that, the set of x values called? That's only x-intercepts, the set of x values, it came up in number 7.
Domain.
Okay, talking about the domain, right? It increased from 0 to 1.5 minutes. That's talking about the domain. I'm going to add some language to this later, but we want to recognize it's increasing over this domain.
Number 2 is what you were on number 1.
That's what I'm writing right now, yeah. Then the coffee what?
Decrease.
Decreased. And what am I going to say for it decreasing?
1.5 to 10.
From 1.5 to 10 minutes.
That's for number 2.
Yeah. Now, you can add extra details in there, okay? But I do want to emphasize that the big thing when I ask you about this increasing, decreasing, am I asking you for the outputs or for the inputs?
Inputs.
I'm asking for the inputs. I'm asking where is it increasing? Where is it decreasing? And so,
Where is that? That's it.
so when you are asked for increase, decrease, respond with domain intervals of increase or decrease. Notice, I told you the x values. I gave you the domain values that it was increasing and decreasing on. Whenever a mathematician, whenever a teacher asks for the intervals of increase or decrease, they're not asking for the outputs, they're asking for the domain intervals, the inputs. Okay? That is what is being asked for. The most common mistake students make is that they tell me the outputs. And hey, for this context, do I care that it went from 70 to 170? Yeah. Could you add that detail in here? Yeah. What do you have to have though? Domain intervals. You can add more detail in, but I have to have the domain intervals. You have to have the domain intervals. Okay? Now, I do want to point out, can you highlight and use markers on an assessment to show yourself and me where the increase and where the decrease are?
Yes.
Even if you get the domain wrong, if you do that, is that showing me that you at least understand a little bit about increase and decrease?
Yes.
Yeah. So please use that to your advantage. That's why I asked you to get this marker out and to highlight like this, because that is a very valid strategy to help both you and me understand or see that you understand increasing and decreasing. Okay? All right. So number 3, what was the temperature of the coffee when she took it out of the microwave?
170.
How did you know it was 170?
That's the highest.
Because it's the highest. I need a better term than just the
That's
highest.
the max.
It's the maximum. Remember how I asked for a third color? Because now we need to highlight that maximum. So like, use a different color. So the maximum temperature was what?
170.
170
Fahrenheit.
degrees Fahrenheit when x equals 1.5 minutes. The best way to write a maximum or minimum is to tell me what the y value is at an x value. Can you just write it as a point? Yes. It is better to write maximum, minimum as it's this output at an input. Because what we're actually asking is what's the maximum value? What's the maximum output or the minimum output? So max or min output at x equals input. So you can write it as a point. I haven't checked on delta math yet. Delta math may ask for it as a point, but it is best to write it as, hey, this is what the maximum value is, this is what the minimum value is at this x value. Okay. One quick word or note, this is language-wise. Do you have that fair model out? Not that one. This one. Yep. Yeah, I wish I thought about this earlier. One quick note that I will point out to you is, bottom right of your fair model, it talks about polynomial domain, range, and intercepts from a graph. We haven't really done domain and range yet, but on the back side, it talks about something called extrema and intervals of increase, decrease. So if you need to add any extra special notes there, that's on your fair model. So increase, decrease, there we go. What does that word extrema make you think of? Extreme, right? What's a word for the points on a graph that would be the extremes? The maximum and minimum. If you ever see that word extrema, it just stands for, it could be a maximum or a minimum. That's all extrema means, okay? Technically it's plural form, so a maximum or a minimum. Extrema is a catch-all term. So, an extremum can mean a maximum or a minimum. So that might be a detail that you want to add in there. Okay. Should I walk? Okay. I'm going to add some more details a little bit later, but I'm good up to this point. Oh wow, I don't remember doing it quite like that. Number 4, how long did she microwave the coffee and how long did it take her to drink the coffee?
It took her she put the time in like 2 minutes.
It wasn't quite 2 minutes.
Finished it 10 minutes later.
Well, so remember, actually here, how long did it take her to heat up the coffee?
1.5.
1.5 minutes, right? That's that domain interval of increase. How long did it take her to drink the coffee?
8.5.
8.5 minutes. Notice it didn't just magically stop at, what was it, 115 or so? It didn't just magically stop at 115. It disappeared because she finished what?
Drinking.
She finished drinking the coffee, right? Okay. So number 5, what was the temperature of her coffee after 6 minutes? Oh, that was something I meant to go back and do really quickly. Sorry, I meant to do this earlier. Does anyone know of a function notation that we could use that would make sense based on this information given? Like, what was my output all about?
Minutes. Well, temperatures.
The temperature, right? Specifically, and so the temperature, T, but what was the input all about? It was the minutes, right? Which is my time. Both have T, maybe, is the temperature of the what?
Coffee.
Coffee. So let's use a C for coffee, T for time. So what would be a function notation to indicate the output was the coffee temp, the input was the time.
D,
Where's the D coming from?
I just said A, B, C, D. I put D.
Okay, so, hold on.
Degrees?
If I say f of x, what's my input?
X.
What's my output?
Yeah.
Okay. So if my input is time,
C of T.
C of t is going to be my function notation. Okay? So sorry, please write that at the top because I'm about to use that. I forgot about that detail. That is not something I expected you to see or know right away. That is something I'm adding on to this. But notice I'm just using symbols that make sense based on the context. So it's the coffee temp. That's the C. The T is my time. So using function notation to describe what is happening here. So coffee temp and time. Do notice DD, I specifically am just talking about that T is my time, right? Like I labeled that T as time. Okay. Number 5, I'm going to erase all this. Hopefully we have all these notes. Okay. Number 5 asks, what was the temperature of her coffee after 6 minutes? So do I have the C right now or do I have the T?
T.
I have the T, right? So how could I write my answer to number 5? You said I have the T, right? The time?
C.
C of...
Box. Wait, hold on. Yeah.
C of... But what is T? It is... Say again, William?
Temperature.
6, thank you.
Yeah.
Guys, in number 5, it says, what was the temperature after what?
6.
6 minutes.
C of 6.
So C of
6.
6. What does C of 6 equal? 130? So when the input is 6, the output is 130? This is number 5, right? A lot of y'all just put 130 degrees Fahrenheit. And guess what? That's perfect. That's what I would expect for number 5. I'm trying to help you see, though, does this tell you more than just writing out 130? Yeah. This is not just telling me 130 degrees Fahrenheit. It's telling me at 6 minutes, and I can even write the minutes in there. At 6 minutes, the temperature was 130 degrees Fahrenheit. This is the function notation at play. It's not just an output, it's also an input. It's not just an output, it's also an input. Oh, that's not what I want to do. Okay, number 6 though. At which times was the temperature of her coffee 145 degrees? And 8, man, y'all had an interesting conversation, at least by the time I had left, because Parker, you were confident. You're like, it's a minute and a half, but Chelsea, you were like, it's 4 minutes. And Parker goes, what? How did you get 4 minutes? Did y'all ever figure out where she got 4 minutes from?
Yeah, we did.
Did y'all, so what was the final answer?
4 minutes.
What you mean by that?
You're close.
Because, like, I don't know, like, cause if you go to 145 and you're all the way over, or that line, you know what I'm saying,
Uh-huh.
come down forward.
Hey, quick question though. Who was right? Chelsea saying that it was 4 minutes, or Parker saying it was a 1.5, up here 1.2 minutes? Who's right?
Both of them.
Heard,
Both of them.
say it again.
Both.
Both of them are right. Neither of you were wrong. Look, it says, what was it? 145. Here's 145. I bring it across. How many times does it hit the graph? Twice. You were both right. But you need to be aware there's more than one answer sometimes. Not if it's a function we're talking about C of t, but here we need to recognize C of, what is that, 1 point, I think I have it, at least looking here, I've got 1 minute, not 1.5, maybe 1.2, I can see that. So C of 1.2 is approximately 145 degrees Fahrenheit, but definitely C of 4 is 145 degrees Fahrenheit. Notice we got 2 answers. You were both right. Okay? So, So please pay attention to that. If you did not notice both answers, add that detail in. Because again, C of 1.2, C of 4, both 145 degrees Fahrenheit. So here's where we're going to wrap up though with this lesson at least. What is an appropriate domain for this function?
0, 10.
So the domain
0, 10.
would be time, right? Because domain is always which values?
X.
The x values. Domain is always x values.
Yep.
And so what's going to be my domain?
0, 10.
0 to 10. And I saw some people do parentheses, and I saw some people do brackets. Which one is it?
Parentheses.
Brackets.
Why brackets?
It reaches.
Cause that's almost, it's like a, what's the name? Like,
They all numbers.
close, it's like,
It touches the point.
yeah, it touches
Okay.
when it's closed.
So it's closed. Okay, I actually do like that language, and I do like what you're saying as well, but I will point out, do we actually have that point? Is it a closed point, a certain,
Yeah.
or is it an open point?
When it's closed.
It's closed. Like, do you actually have 0 minutes on this graph?
Yes.
Yeah. If you actually have it, then you need a bracket. Do you actually, does the coffee ever get to 10 minutes?
Yes.
Yes. So you need a bracket. So what about the range? The coffee temperature. Okay, so the temp, which is my outputs or y values. And so what do I need there? Why only 70? Why did you go all the way down to 0? Yeah.
It always starts, it starts. It don't go all the way down.
I will say this, and be careful, it's not just that it starts at 70. 70 is the what? There's a key word I'm looking for.
Y-intercept.
It's the minimum. It's not the y-intercept, it is the minimum. Because I could have a lower y value than 70, but do we have a lower y value than 70?
No.
No. So remember, when we do our interval notation, what always goes first? The minimum, then the maximum. This 0, is that the minimum time? Yeah. Is 10 the maximum time?
Yes.
Guys, when you use interval notation, it's always a minimum to maximum, and then you have to know, is it x values or is it y values?
Can you say a question?
I wasn't asking a question. I was just saying, you have to know if it's always minimum to maximum, you have to know, is it x values or is it y values? Okay. Alright, last question. Does the coffee cool at the same rate that it heats up at? How do you know? And slowly. So, does anyone know what a term we could use for that rate there?
Constant rate.
It could be a constant, but let's look at this again. That actually is a constant rate of change because it's what shape?
Linear.
Linear, okay? Is that linear?
No.
No, so it's not a constant rate of change. It may be exponential. Actually, it probably is based on Newton's law of thermodynamics. It plays into it. So it is exponential, but I was just going to say this, the average rate of change. The average rate of change is just slope, okay? So when we say, is it the same rate, think average from beginning to end. And when we say the average from beginning to end, we're just talking about the slope. So if you're asked, hey, does it have the same rate like this, and there are two different types of functions, you just need to think about the average rate of change. And so when I look here, is that slope more or less than this slope?
More.
That's definitely more, right?
Yes.
It's steeper. So this has a steeper slope than this does. So it cools slower because the average rate of change is not as steep. Notice I didn't talk about the positive or negative, because if it's positive, it's telling us the graph is what? If the average rate of change is positive, it tells us the graph is
Linear. I mean, I know,
Rising.
what's that more mathematical term? Increasing. And if the average rate of change is negative, it tells us it is decreasing. So that's what is being told there. Alright. I want to make sure I get all the quick notes. So we're going to do quick notes on the back. I want to make sure I have all the stuff that I wrote out. Okay? Alright. Alright, hey guys, this is a huge summary of everything you need to know about analyzing a graph. First things first. A graph of a function can be used to ID what? What was the first thing we identified on that graph? For number one, it was the
Degrees.
nope,
Temperature.
nope,
Of the coffee.
nope.
The microwave.
Dog, look at number one. What did we look at? No, it was the y. Starting point, so the y-intercept. Guys, the graph of a function can be used to ID one, the y-intercept. That's f of 0.
Can you please release all varsity boys basketball? Thank you.
So where input is 0. Okay.
Top third on the
What
fourth
else? What else can we identify? Not just a y-intercept. We didn't do it this time, but also an x-intercept. This is where the output is. Make sure you get this from somebody. Where the output is what?
10.
Thank you. X-intercepts are where the output is 0. So that's where f of x equals 0. By the way, what's another word we can use for those x-intercepts where f of x equals 0?
CNT. Another word. C.
The x-intercepts where the output is 0. Those are also called zeros, right? I guess. We've heard it for a few weeks, maybe a couple of months now. Okay? So the maximum values, what I do want to point out is, and so maximum values are the highest output. How did we know on the graph when we had that maximum value? Because what did the function stop doing?
Can you restate it?
The maximum value, it was when the function stopped. Stopped what though?
Maximum.
Stopped, what's it doing here?
Stop rising.
What's a better term? Increasing. It stopped increasing and started to decrease, right? You're going to have a maximum when function stops increasing and starts decreasing. Yeah. So when do we have a minimum? That's my lowest output, and that's when the function what? And fourth law. 145 is what I heard. So when is it a minimum? When the function stops? Stops what? Minimum. Stops decreasing and starts to increase. Right? Decrease, then increase. It's a great joke. Good job. Sorry.
Hey, what's she even say? Why did the chicken cross the road to get to the other side?
Okay. Domain intervals of increase and decrease. When I ask you for the domain intervals of increase, decrease, are you supposed to give me the inputs or outputs? I say, didn't we do the time, the inputs?
There will be a mandatory track and field meeting on Thursday, at 3:30 in the front. Anyone wants to try out?
Boys and girls soccer players and all bowling players
Highlight your increase and decrease.
at 2:45 for 2
Attention all students and teachers. We will be selling basketball tickets for the in-school games at lunch. So make sure you buy your tickets. The tickets are $7.
Finally, the domain is all what?
Be there or be square. 'Cause it's
X-intercept.
basketball.
Not x-intercepts,
X values.
x values, or
On Thursday, or not, the choice is yours.
what else can we call those x values? It's only zeros if it's an
Inputs.
x-intercept. Inputs. And range,
Outputs. Y value outputs.
and what are we gonna use to report the domain and range? Use interval
Notation.
notation. Remember, that's where you have a minimum value and then a
Maximum value.
By the way, this interval notation is what you're gonna use for increase and decrease as well. I'm gonna have y'all work to start tomorrow on that check your understanding. And then I'm gonna have y'all do, hold on a second, that's on there, y'all are gonna work on that in small groups. I'll give you 10 to 15 minutes on that, and then I'll send out the answer key for you to check yourself. And then after that, it will be a Delta Math assignment where you are finding x-intercepts, y-intercepts, maximum, minimum, domain intervals of increase, decrease, and domain and range. So tomorrow's gonna be all about practicing this. I might put some converting factor to standard form on there as well.
Doesn't matter.
Yep, Delta Math. I'll send an email to everybody as well to confirm the assignment.